Right. So the motivation of this lecture is to understand why metals are shiny and why semiconductors are absorbing and why insulators are transparent. Okay. And we want to understand this in connection with its electronic properties. And then they are highly related. Metals are reflecting because they have free electrons. And semiconductors are absorbing because they have an appropriate amount of band gap. And the insulators are transparent because they have a huge band gap. But I just want to talk a little more detail about all these things so that you get some sense why materials shows general optical properties. So in order to know that, you need to first understand this permittivity thing. Okay, so the permittivity is again this, we call this epsilon. The relative permittivity is epsilon. Is 1 plus chi. Chi is electric susceptibility, right? So 1 is just one. It's just a vacuum response. Plus chi is the electric susceptibility. So the chi connects E and P, electric field to the polarization, right? So it just tells you that your how your material is polarized, how much your material is polarized to a applied electric field. So this is a response of bound charges to the applied electric field, right? It's like this, it's polarization. And there's a similar concept, but it's different. It's conductivity, right? So conductivity, so here the permittivity is typically discussed in the context of insulating material, right? There's no current flow, but material is gonna be polarized. And then this chi measures how much this material is polarized. And conductivity is typically defined for conducting materials, not the insulators. So that if you apply the electric field, electrons are moving and making a constant flow of current, right? And the conductivity tells you how much of current you have for a given electric field, right? So this, in a sense, is a response of free charges to the applied electric field. So one is about the bound charges. Because it's bound to the atom, it cannot just move around, but it can be polarized. And here, at the response of free charges can move like freely so that you have current. And then if you look at the permittivity and conductivity in a deeper level, the polarization is about the displacement of electrons with respect to the lattice atoms, right? So the situation is like this. If you want to describe polarization, you have atomic lattice and you have electron clouds displaced like this. Then you have displacement, delta X. I'm sorry, it's just the X, displacement. So that this displacement determines how much your atom is polarized, right? And on the other hand, if you want to measure current, if you want to describe current using your carrier density and elementary charge and X, it's about the velocity or speed of electrons. So you have a constant speed of electrons, and then that creates current. So if you look at this, you can connect these two. So current is actually time derivative of polarization field, current density. Okay, so in a frequency domain, if you just do a Fourier transformation, then current is just a minus I omega p omega, right? So they are proportional to each other. So in that sense, permittivity and conductivity are connected, right? So you can make, you can write this relation. Your permittivity can be written as a, 1 plus I conductivity divided by epsilon omega, right? So what I want to say here is that if you go to a high frequency, epsilon, the permittivity and the conductivity are not just a completely different concept, but they can be described in a unified frame, which can be written like this. Okay, so conductivity is about the current flow, and the permittivity is about the polarization. But if you go to the AC case, they are connected.